Hello, and welcome to this tutorial series on 3D printing at the nanoscale using f3ast. In this video, we'll see how to use f3ast to extract the required calibration parameters to model febit growth and build 3D structures with f3ast. This video assumes that you followed the previous tutorial video where we pulled the repository onto our computer and installed f3ast package. If that's the case, let's head over to Projects folder. Here I have the project opened in VS Code, but you can open it in the editor of your choice. The important folder for this tutorial is the examples folder, where we have a calibration Jupyter notebook. I'm going to open the notebook here directly in VS Code, but you can use the regular Jupyter notebook interface. Importantly, we need to use the environment where f3ast is installed. The first cell just imports some libraries together with f3ast. And then the first real cell we use to export the calibration structures that we call vertical calibration. And this consists of a grid of 5 by 3 vertical structures, where the shortest one takes a total of 1 second to build, and the longest one total of 15 seconds to build. You can adjust these values to be longer or shorter depending on how fast febit growth is on your system. Running this cell exports two files. The first one is a stream file that you should import into your microscope and run. The second file is a data file that defines where the structures are and how long they take to build. We position the structures randomly in the grid so to avoid any transient effects. Next, once the structures have been built in the microscope, you should take an image of them at a high tilt. Usually around 45 degrees tilt is enough. Here we point to the image of the structures and the data path to the corresponding data file that was exported together with the stream file. Running this just imports the image. It's also good to take an image at a slight rotation to the grid so that the structures are individually visible and there is no overlap. Next, we need to define the scale bar. First, we use this code to set the real scale bar size. And then running the cell, we can select the start and end of the scale bar. And with this, in the next cell, we can calculate the pixels per micrometer value, which now the software can use to analyze the image. Next, we process the calibration image. First, we remove the bottom bar containing the scale bar and additional information. And then we threshold the structures to separate them from the background. With this, we can label images. We can label the image and label individual structures. And then also filter some of the smaller structures. Sometimes the background noise gives some false positive signals. With this, we can see that the software has identified 13 wires. The two smaller wires have been discarded because they're also probably very noisy. And without them, we have a total of 13 wires that we can use to fit our calibration. We can get the length of these wires using the pixel per nanometer value that we have, as well as the observing angle or observing tilt. With all of this, now we have the total lengths of all of the wires and their dwell times, so we can fit the calibration. Here we are using our distortion dominated model, and we get two values, the growth rate and the effective heating parameter K. We can see that in this case, the calibration data very nicely fits the fit parameters. In addition to this, we also need the effective beam width, or sigma. And for this, we build a sequence of wider wires at a particular angle, and we try to match that angle to the single pixel wire. If the sigma value is correct, the wide wire and the single pixel wire should have the same angle. So here we set some set of sigmas. It's usually somewhere between 3 and 6 nanometers where the sigma is. And then running the cell, we'll export the sigma calibration file here as a stream file. And we can see here that it should look like as a set of wide structures and then one single pixel structure. When we take an image of it at a tilt, it should look like something like this, where here we have a single pixel wire and a set of wide wires, and we should match the angle of the wide wire to the single pixel wire to get the correct value of the sigma. This analyzing this image is not automized because it doesn't have to be done very frequently. The sigma value is pretty consistent and it's fine to reuse between different sessions on the same microscope, barring any bigger changes. So with this, we have all three parameters that we need to now build the structures. And in the next video, this is what we're going to do. We're going to start exporting some example streams using these calibration parameters. Thanks for watching. I hope you found this useful. I'll see you in the next video.